So now let's define a relation R. Any relation R from A to B is defined as subset are equal to A cross B. This is a fundamental definition of any relation. Okay, so that means any relation is one of the subset of this A cross B, where A cross B is a Cartesian product of AB. Let's see one example. Let's say A is 1 to 3 and B is ABC. Okay, let's say this is A, this is B. Then what is A cross B? A cross B is nothing but largest mappings. That means you try to map every element to every element. Whatever you get, that is called A cross B. That means this is the highest size of mapping: 2A, 2B, 2C, 3A, 3B, 3C. No one can map better than this, isn't it? That is called A cross B. So what I want to say is, any relation you form that should take edges from or mappings from this A cross B. No one can take any different edge than this one, isn't it? That's why I can say that any relation is subset are equal to A cross B. This is A cross B. Understand? So that's why. Now let me write this A cross B in set form. You get 1 comma A and 1 comma B, 1 comma C, 2 comma A, 2 comma B, 2 comma C. In the same way, 3A, 3B, 3C. So this is A cross B. Now I want to form one relation, random relation. Let's say R1. That R1 is nothing but, according to the definition, you take some subset of A cross B. Let's take some subset. I take 1 comma N and I take 1 comma B and I take 3 comma C. So quite random. Okay. If I do that, I form a relation. Let's take one more relation R2 by not taking anything. I don't take anything. Still that empty set is subset are equal to A cross B, isn't it? These two a relation and R1 also relation. Now you can have multiple relations like this. Let's go to one more relation R3, which is nothing but I take every element 1A, 1B, 1C, okay, 2A, 2B, 2C, and 3A, 3B, 3C. If I do that, I form a relation, isn't it? Why this is relation? Because this is subset are equal to A cross B. So every set is subset are equal to itself. That's why R3 also a relation. Okay. Now there are so many relations from A to B. So everything is one subset of A cross B. So here one interesting question is, how many such relations you can form? You want to know, then what you do is ask yourself how many subsets you can form for A cross B, because every relation is supposed to be subset are equal to A cross B. So problem is reduced to how many subsets you can form for A cross B. We know that if any set contains k elements, any set contains k elements, there are 2 power k subsets, right? Now the question is, how many subsets A cross B can contain? For that we should know how many elements A cross B contains. A cross B contains mod A into mod B elements, isn't it? Mod A into mod B elements. We know that, correct? So that is nothing but mod A mod B. Now, if a set contains k elements, there are 2 power k subsets. If a set contains AB elements, there should be 2 power A into B subsets, isn't it? Okay. Each one is definitely a relation because it is a subset of A cross B. So finally, we got a number of relations, right? The total number of relations from A to B is, from now onwards, 2 to the power of mod A into mod B, where mod A is number of elements in A and mod B is number of elements in B. Understand? Let's for some time talk about relations on set A. That means relations from set A to set A. So whenever I have a relation from set A to set A, I say that is relation on set A. That means domain and codomain is same. When you have such relations, then we can define these properties: reflexive property, symmetric property, transitive, anti-symmetric, asymmetric, and irreflexive. We'll see one by one. So what is reflexive property? Let me define what is reflexive property. For every element A belongs to your domain, So you know that now you have set A, which is domain, and codomain also A. Okay, so now relation is from A to A. Reflexive property is nothing but for every element of your domain, what should happen is A comma A should belongs to your relation R. That's it, very simple. For every element of your domain, A comma A should belongs to R. Example, let's say domain A is 1 to 3, then automatically codomain also 1 to 3, isn't it? If I have 1 to 1, 2 to 2, 3 to 3, but you can have extra also, like 3 to 2, maybe 2 to 1, doesn't matter. Let's consider this mapping. I write in set form, then it will become 1 comma 1, 2 comma 2, 3 comma 3, and 2 comma 1 and 3 comma 2, isn't it? This one, consider this one. So this relation is reflexive because it satisfies reflexive property. So this is the property which is reflexive for every element of your domain. That means for every element means 1, 2, 3. What should happen is 1 comma 1 should belongs to R, 2 comma 2 belongs to R, 3 comma 3 belongs to R, right? So A comma A should belongs to R for every element. Then 1 1 2 2 3 3 definitely should belongs to our relation R. That is what we have now. Other elements, this formula or property is not talking about other elements. That means you may have, may not have. That's why this is reflexive relation. Any relation which satisfies reflexive property is called reflexive relation. Then I can say that this is reflexive relation. Otherwise I can say this satisfies reflexive property. We'll see one more example. R equal to, let's say 1 1 and 2 2 and 1 comma 2 2 comma 1. Is it reflexive? No. First know the domain. Your domain is 1 comma 2 comma 3. Then you have only 1 1 and 2 2 and 3 comma 3 is missing. That's the reason this relation cannot be reflexive. So given a description of the relation, given a set form of a relation, always we can easily check whether it is reflexive or not. But sometimes they give you description of the relation. We'll see that. The description of relation will be like this. Let's say R of x equal to like x square. They give like this. Otherwise they give like this. A relates to B if and only if A plus B equal to even. So in these two forms they can define a relation. So here R of x equal to x square means x is mapped to x square. Okay, that means x is related to x square. All are same. Now if I say like that, A relates to B if and only if A plus B is even, that means whenever the sum of two numbers is even number, then I am relating A comma B. In that way you can understand about mappings. Okay, let's consider this one. A relates to B if and only if A plus B equal to even. Okay, then if they give this kind of form, then how to check whether the relation which is given is reflexive? Okay, since domain is not mentioned, we have to fix one domain. Okay, of course they mention the domain. Let me fix the domain here. Since we are talking about parity like even and odd, right? So probably this would be good integers, isn't it? Okay, for given domain integers, is this relation reflexive or not? We have to check. Let's do that. So I do this with two methods. One is informal method. I take some integers and I check. Let's take integer number 1, integer 2, integer 3, and we know that there are so many such integers. Okay, and I take 1 comma 2 comma 3 here, and I will check whether 1 is mapped to 1 or not and 2 is mapped to 2, so on. If this 1 2 3 maps to themselves like 1 to 1, 2 to 2, 3 to 3, that is called reflexive property, right? We'll see that. Let's read this relation with 1. 1 relates to 1 if and only if 1 plus 1 is even. Okay, since 1 plus 1 is even, this is true. If this is true, because of if and only if, definitely 1 should be related to 1. That is the meaning of if and only if, right? Whenever I write a definition with if and only if left is true, right is true, left is false, right is false. If left is true, right is false, what happens is it is double implication. True double implication, false is false. But we know that this is the definition, that definition cannot be false. Whenever I say something is definition, we should treat the definition as true statement. Okay. So if really this statement is true statement, since already a plus b is even number, then 1 definitely should be related to 1. That's why I can say that 1 is related to 1. Similarly, 2 plus 2 equal to even number. This is true. True double implication, true, only true. That's why this should be true. What is that? A related to B should be true. For that 2 should be related to 2. In that way we can understand that whenever right is true, left should be true. If 3 plus 3 is even, 3 should be related to 3. That is what definition says. Understand that point? Then by observing this example, I can say that 1 is related to 1, 2, 3. So we have confidence that now every element is related to itself. That's why this kind of relations are reflexive. Okay. So I will tell you one more method here to check whether a relation is reflexive or not. How I do is, let me say, take the same relation. A relates to B if and only if A plus B equal to even number, right? Okay. Domain is integers. Let's represent an integer with x. So that means I am covering every integer now. Though I am taking one integer, I am covering every integer because I am taking a random variable x. So it covers every possibility, every possible integer. Then our proof should be x related to x, isn't it? But we know that x is related to x. I am just writing the definition. X is related to x if and only if x plus x equal to even. Let's try that. X plus x is 2 into x, which is equal to even number. Whenever x is integer, because domain is integer, then x could take only integers. Then 2 into integer is always even number, isn't it? Whatever the integer you take, 2 into 3, 6, 2 into 7, 14, 2 into minus 5, minus 7, everything is even number. So whenever this is true, we know that already I told you that whenever you write if and only if for a definition, when right is true, left should be true, then x is related to x. That means x is mapped to x. I proved that x is mapped to x for a particular x, of course, but this is not a specific one, isn't it? So x covers every integer. I have not assumed any property of integer, so that's why x covers every integer. Then x is related to x for every x, isn't it? That is what the definition of reflexive property. So reflexive property is satisfied. Okay, so we'll see one more important thing in this reflexive properties. In exam, they give you two kinds of questions. One is they give you a description like this and they ask whether the relation is reflexive or not. Second thing, they ask the number of reflexive relations possible on a set A. We'll see that kind of problem now. The number of reflexive relations on set of n elements. How to solve this problem? Let me take A as that set 1, 2, 3, so on n. Okay. Before solving this problem, I begin with number of just relations, not reflexive relations. Okay, let me solve this problem. How many relations possible on set of n elements? After that, I will come to number of reflexive relations, because the process what I am going to follow to solve number of relations is going to help us in solving this problem. Let's begin with number of relations. Let me take a set with just 3 elements rather than n elements, okay, so that we can extend the problem to n elements later on. If I solve this problem, it will be easy for me. If A equal to 1, 2, 3, then A cross A will be 1, 1, 2, 2, 3, 3 and 1, 2, 2, 1, 1, 3, 3, 1 and 2, 3, 3, 2, isn't it? Yes. Now we know that any relation is just subset or equal to A cross A, isn't it? Okay. Now to understand this problem very clearly, I usually connect my problems with real world objects. Let me imagine all these elements as teachers. Okay. So now A cross A is nothing but some teachers. Now what is R? A cross A is teachers. R is some subset are equal to teachers. That means I can say committee, right? So you have to form a committee now. How many committees you can form is the question. Okay. So you tell me what is the property of any random committee. Think about it. So any committee generally contains some of the elements of this all elements, isn't it? Okay. You tell me, if I give you one box, okay, otherwise a box, let's say, and this is a very big box which contains teachers. How many teachers? 9 teachers. You have to pick some teachers, any number of teachers. Then how you do it? Systematically. Think about it. Probably that systematical way will be like this. Go to teacher number 1, ask. He may come, he may not come, because every teacher has two options, right? Because you are forming a random committee, right? Not a fixed committee. So that's why every teacher has two options. He may come, may not come. Okay. Then go to every teacher and ask. If he comes, then fill here. Otherwise, leave him. Go to second teacher and invite. If he comes, then add him. Otherwise, don't add. In that way, go to every teacher and invite, right? So that is a task sequence. If you follow, then that task sequence is going to form any relation. Yes or no? Example, I want a relation where I want only 1 1 2 2 3 3. How you would do? How this task sequence will work? Let me write the task sequence. What is that? Invite T11 followed by invite T22 followed by invite T33, so on, right? Okay. So if you want only 1 1 2 2 3 3 into your box, that is possible, because when you invite, there is a chance that 1 1 comes, 2 2 comes, 3 3 comes. In that possibility, you get your desired relation called 1 1 2 2 3 3. So in that way, what I want to say is, you can have any dream relation by following this task sequence, correct? If you want all, that is also possible. When every teacher want to come, like, because there are two options. One is they come, second one they don't come. What if everyone comes? Like, when you invite T11, what if he comes and T22 comes, everyone comes, then your relation will become full. In that way, so what I want to say is, this task sequence if you follow, definitely every relation can be generated, isn't it? Now the question, how many such relations are possible? According to product rule, the total number of ways of forming relations equal to cardinality of T11, that means total number of ways of doing T11 into total number of ways of doing T22 into total number of ways of doing T33, so on. Product rule, correct? And they are all independent. If 1 1 comes, still 2 2 can come. If 1 1 doesn't come, still 2 2 can come, isn't it? That's why these are all tasks are independent. Now let's do this problem. The total number of ways of forming relations equal to total number of ways of selecting 1 1 2 into total number of ways of selecting 2 2 2. In that way, every element has two options, 2 into 2 into 2 into 2 into how many times? 9 times. That's why there are 2 to the power of 9 ways we can form relations. In simple words, now I will tell you in single line. The total number of relations are nothing but they depend on number of elements. Since each element has two options, the total number of options for overall altogether is 2 to the power of 9. Since every element has two options. You understand that point? That's why there are 2 to the power of 9 ways they can vary their decisions, then 2 power 9 ways. Now come to our problem. Our problem is number of reflexive relations, isn't it? So how number of reflexive relations problem is related to total number of relations, we'll see. Now you have A cross A, 1 1 2 2 3 3 1 2 2 1 1 3 3 1 2 3 3 2, isn't it? Now to form a reflexive relation, we have to select few objects from A cross A, but the compulsory thing is 1 1 is compulsory, 2 2 is compulsory, 3 3 is compulsory. Let's follow the same technique like number of relations technique. How you do the task sequence? So forming a relation can be simulated by this task sequence, correct or not? So total number of relations equal to How many ways you can select T11? How many different ways you can select T22? How many different ways you can select T33? Followed by how many different ways you can select T12, so on. Okay. So these tasks are 9. Remember, 1, 2, 3 up to 9. 4. Okay. First task. How many different ways you can take 1 to form a reflexive relation? So 1 is compulsory, isn't it? So there is no option for you. We have to take it. Correct? In the same way, 2 has to be selected, 3 has to be selected. Better what you do is directly take them. It's like now the question, you have 9 teachers, these 3 teachers are compulsory, then how many different ways you can form a committee? It's simple. How many different ways you can select these 6 teachers matters, isn't it? We know that every teacher can be varied in 2 ways. Then 2 to the power of 6. What about these 3? This entire unit should be taken. Just take it in one way into, that means 1 into 1 into 1, 1 into the remaining 6. So each remaining element can be taken in 2 ways. That's why 2 to the power of 6. Isn't it? 2 to the power of 6. Let's generalize it for n elements. In general case, what happens? You will have n square elements, isn't it? So A cross A contains n square elements. Out of them, this 1 1 2 2 3 3 up to nn, let me call them reflexive kind of elements, a comma a. They are n, isn't it? Out of n square, if I remove that n, remaining elements are n square minus n. Now come back to our way. We take all that group one way, right? Into the remaining elements are like n square minus n. Each element has two options, 2 into 2 into how many times? N square minus n times. That would become 2 to the power of n square minus n, isn't it? So that's why the total number of reflexive relations are 2 to the power of n square minus n. The significance of n square minus n is other teachers, like that means other than this reflexive kind of teachers, 1 1 2 2 so on up to nn. They are n, overall n square. If I remove that n, remaining elements are this n square n minus n. Every element has two options. That's why 2 power n square minus n. Okay. Let's see the second property, symmetric property. So symmetric property definition is like this. For every two elements a comma b belongs to your domain, if a relates to b, then definitely b relates to a. We know that a relates to b can be alternatively written as a comma b belongs to r, isn't it? That means a relates to b, then a comma belongs to r, then b comma a belongs to r. Both are same. So this is the definition of symmetric property. You should not violate this definition for any two elements. Remember, this definition says that whatever the elements you take, a comma b, that a comma b may be same also. Okay, whatever the elements you take, if a comma b group belongs to R, then b comma a should belongs to R. It doesn't mean that a comma b has to be in R. If AB belongs to R, then definitely B comma A should belongs to R. That's the concept of symmetric property. We'll see one example. Example, let's say your relation R equal to 1 comma 2, 1 comma 3, 3 comma 1. So this is not symmetric. Why? This relation is going to violate this definition. We'll see that. Let's substitute 1 comma 2 in the relation. So the rule says that if 1 is related to 2, yes, 1 is related to 2, true, then B related to A. What is B here? This is A, this is B, right? A comma B belongs to R, then B comma A should belongs to R, where B comma A is 2 comma 1, then 2 comma 1 belongs to R is false, isn't it? Then I got true, then false. True implies false in logic is false. That means definition is violated. If any relation violates the definition, that cannot be symmetric relation. That's why this is not symmetric relation. Okay. So I will give you one very important point about symmetric relations. Whenever a relation is not symmetric, okay, let's imagine your relation as a box. Okay. then whenever your relation is not symmetric, we can easily prove that one A comma B belongs to R like this, and B comma A is outside, does not belongs to R. Okay, this is compulsory. If you cannot show this, then we can't say that that relation is symmetric. Okay, whenever you show this, definitely that is not symmetric. Understand that point. Let's take one more example. This one, empty set. So this empty set is symmetric. The reason, if really it is not symmetric, show me this kind of two elements where A comma B inside the relation, B comma A outside the relation. Since we don't have any element, how can I show that kind of counter example? No, I can't show this kind of example, right? So when you can't show this structure, then definitely the relation should be symmetric. And the rule says that if AB belongs to R, I don't have anything in my relation, then I never satisfy AB belongs to R, right? Then AB belongs to R is always false. Then false implies anything in logic true. False implies true, true. False implies false, true. That's why. So always my empty relation is symmetric. Okay. Now one more example. 1 comma 1. So there is no problem with 1 comma 1. Just check it out. If 1 1 belongs to R, then 1 1 belongs to R. Obvious, it is true. 1 1 belongs to R, true. Now for this example, reverse also true, right? B comma A. So a symmetric relation can have 1 comma 1 without any violation. Okay, this is about symmetric property. So in the exam, they will give you description of the relation. Example, A is related to B if and only if A plus B is even number, let's say. Let's domain is integers. Then is this relation symmetric? Let's try. So how to prove that this relation symmetric, I will tell you. I take the definition and I prove that definition is true. If I violate the definition, then this cannot be symmetric. Let's begin. What is the definition? If A relates to B, then we have to prove that B relates to A. Really this definition is wrong. There is only one case, that is A relates to B should be true, B relates to A should be false. We know that if P, this is like if formula, then formula. If something, then something. Whenever your definition is in this form, then this is true, this is false, then only overall will become false, because true implies false is the only way we can make this kind of definitions false. Remember it. Okay, so if you don't understand this concept, then you are having a problem with logic, then please go through proposition logic first before coming here. Okay, so this is if P then Q. Whenever you have if P then Q as a definition, P true Q false is the only way we can make the definition false. That's why. Let's try it. But even A relates to B is true, definitely what happens according to the definition, A relates to B if and only if A plus B equal to even. If A relates to B is true, A plus B equal to even also true. No one can deny it. Let me take it. If A plus B is even, then B plus A also even. That is also true. Yes or no? Yes. So finally, when A relates to B is true, A plus B is even according to the definition of the relation. A plus B is even, then B plus A is even according to commutative property of addition. A plus B even, then definitely B plus A even. Then this is true. If B plus A even, according to the definition you see. B plus A even, let's read it. According to the definition of this relation, B plus A is even, then definitely B should be related to A if and only if property. That's why automatically B relates to A. Then saying that it is false is impossible, because directly I got B relates to A. True, right? See now, I took A relates to be true, then A plus B is even, then B plus A even. If B plus A even, then B is related to A. That is the definition of the relation. So B relates to A is true. But you said you will make it false. That is impossible, isn't it? That's why this definition is always true. You tried to make true false case, but you did not get. End of the day, you got B relates to A as true. Understand? Let's take one more example and do the same. So this is a new relation. Let's take domain as natural numbers. Okay, natural numbers. For this domain, this relation A is related to B, A is related to B, if and only if A is divisible by B. Example, 2 is divisible by 4. No, right? False. If and only if A is related to B. That since 2 divides 4, 2 is divisible by 4 is false, then A is also not related to B. Okay, just we are understanding the definition of relation. Since 9 is divisible by 3, right? 9 is divisible by 3. So, if and only if 9 is related to 3. So, according to this definition, 9 should be related to 3. The reason 9 is divisible by 3. So, with this concept, we'll see this relation satisfies symmetric property or not. Let's come to symmetric definition. What is symmetric definition? A relates to B, then we have to prove that B relates to A, isn't it? For that A relates to B should be taken as true. If really A relates to B is true, then A should be divisible by B. So that means I can say that A is divisible by B. Let me use this symbol for divisibility. A is divisible by B. Now, can we prove that whenever A is divisible by B, B is also divisible by A? I don't think so, right? Example, 9 is divisible by 3. It doesn't mean that 3 is also divisible by 3, correct? So that's a reason. So this property is not symmetric. It is violating the symmetric definition, you see. This is true, this is false. Whenever you get true false case here, then we are violating the symmetric property definition. We'll see one more example. A is related to B if and only if A is subset or equal to B. Let's take domain as collection of sets. Okay, collection of sets. That means each element in your relation is like each element in the domain is a set. Let's consider one example. 1 comma 2 is A and B as 2 comma 3. Okay. Since A is not subset or equal to B, then this is false. So false if and only if dash is true, false. That means A is related to B also supposed to be false. Then only this definition will become true. Already I told you this definition, our target. One more example is collection of sets. If I have collection of sets, let me take domain A as collection of sets. That means here elements are sets. We are going to map sets. Now let me define relation like this. A set S1 is related to S2. This is what the relation definition. If and only if S1 subset are equal to S2. Okay. Now for this example, is it symmetric or not? We'll see. Let's begin. We know the definition of symmetric property, right? What is that? Write it. If S1 is related to S2, we have to prove that S2 is related to S1. If you can prove it always, then that relation is symmetric. Let's do it. If really S1 related to S2, we know that S1 subset are equal to S2, correct? It's 100% sure. This is the only information you have. With that, you have to conclude that S2 related to S1. So for that, indirectly, S2 is related to S1 according to the definition if and only if S2 subset are equal to S1. That means you have to prove that S2 is subset are equal to S1. Given a condition like S1 subset are equal to S2, can we always conclude that S2 subset are equal to S1? I don't think so. I got one example where this is true, this is false. That is enough to prove that this definition is false. That is S1 equal to 1, 2. Let's take S2 as 1, 2, 3. 1, 2 set is subset are equal to 1, 2, 3. That means this is true. Now S2, which is 1, 2, 3, subset are equal to 1, 2 is absolutely false, isn't it? So finally this is false, right? So collection of sets and the relation is subset are equal to is not symmetric. Okay, in that way. So given any relation, we can check something is symmetric or not. We'll see one interesting problem here related to symmetric property, that is the number of symmetric relations on set of n elements. That's it. Options are 2 power n, 2 power n into n minus 1, 2 power n square plus n by 2, 2 power n square minus n by 2. So we know that, how to solve any problem related to relations, correct? First of all, we take a equal to 1 to 3. Though the number of elements are n, I take 3 first. Then we write a cross a first, isn't it? A cross a is 1 1, 2 2, 3 3, and 1 2, 2 1, and 1 3 3 1, 2 3 3 2, right? Okay. What is my claim is, in any symmetric relation 1 1 may present, may not present, right? If you take 1 1, you should take BA, which is 1 1. That means that is obvious. If you don't take 1 1, still it's okay, right? So that's why by taking or rejecting 1 1, you are not violating the symmetric property. In the same way 2 2 and 3 3. But 1 2 and 2 1 are related. If you take 1 2, you should take 2 1. If you take 2 1, if you take 1 2, you should take 1 2. And if you don't take anything like 1 to 2 1, still it's okay, right? We'll see the relation definition again. If A related to B, then B related to A. Okay, let's take all possibilities. I am just focusing on this group. In this group, if you take 1 2 and if you don't take 2 1, what happens? This will become true, since 1 is related to 2, but 2 is related to 1 is false. Then true false case arises, then it is violating the symmetric definition. So this case is not possible. What is that? Taking 1 2 and rejecting 2 1. Similarly, I can prove that taking 2 1 and rejecting 1 2 also violates the property. Now let's take 1 2 and 2 1 at a time. What happens? A rule says that if 1 related to 2, then 2 should be related to 1, then it will become true and true. True implies true is true, then definition is satisfied, then it is correct. Now for the last one, that is don't take anything. Okay, if you don't take anything empty, then what happens? A relates to B will become false. B related to A also will become false, isn't it? So still false implies false. In logic, false implies false is true. That means if you don't take anything, still you are satisfying the symmetric property. See the rule. Symmetric property is nothing but this rule, right? So if you don't take 1 related to 2, example 1 related to is false now, right? Then 2 is related to 1 also false. Then false implies false is true. What I want to say is, don't take anything, still you can form symmetric relation, right? So how many options you have for this entire group? 2 options, 1 to 2 1, second one nothing, but don't do these two. Now at the same way, we can say that this group also have 2 options, this group also have 2 options. Now according to product rule, the total number of symmetric relations are, it depends on these 3, right? These 3 and these groups. 1 1 can be taken in 2 ways, 2 2 can be taken in 2 ways, 3 3 can be taken in 2 ways. These groups, each group, there are 3 groups, can be taken in 2 into 2 into 2 ways, not 4 into 4 into 4, right? So this is a formula. These 3 represents, this reflexive kind of elements. These 3 represents these groups. Let's generalize it. In general case, what happens? You will have A cross A that contains n square elements, right? So 1 1, 2 2. So this kind of n elements, and remaining groups like 1 2 2 1, sorry 1 2 2 1, 2 3 3 2. This kind of groups, right? We know that these elements are n, and how many groups can be formed? Total elements in these groups equal to n square minus n, isn't it? Because total n square elements out of this n, if you remove n square minus n, then you are forming a group for each individual, each 2 elements, right? Then you divide it by 2, then you get number of groups, correct? Simple. If you have 8 elements, how many groups can be formed? If you take 2 elements in group, definitely 4. That means 8 by 2. At the same way, so this will be n square minus n by 2. Understand? Now let's come to the problem. The formula is 2 into 2 into 2, how many times? N times. We have n elements now, 2 power n into 2 into 2 into 2 equal to, I mean these 2's are equal to the number of groups times. The number of groups here equal to n square minus n by 2, that's why 2 power n square minus n by 2. If you simplify it, you get 2 power n into, 2 power n into 2 power n square minus n by 2 can be written as 2 power n plus n square minus n by 2, isn't it? N square minus n by 2, because when bases are equal, when there is a multiplication between two powers, when bases are equal, powers can be added. Then if I add powers, you get n plus n square minus n by 2. If I simplify it, you get n square plus n by 2. So that's why option C is the right choice. So I just simplified it. Okay, now transitive property, which is third property, it is like this. If an element A is related to B, comma, an element B is related to C, then definitely A is related to C. This is called transitive property. So I can write in a different way, of course, but without losing the meaning. If A is related to B and B is related to C, then we have to prove that A is related to C. Then only that will become transitive. Okay, since it is a definition of transitive property. So how to imagine this relation? Take a bag. This is your relation, and if you have A comma B in your bag, okay, and B comma C in your bag, according to the definition, this will become true. This will become true. Now, if this is false, definition will be violated. Let's say we'll try to intentionally make this formula false. For that, A is related to C should be false. Okay, then A comma C should be outside. So remember, from now onwards, to prove that this formula is false, we have only this case, and in this case what happens is, you will see some two combinations of elements A comma B, B comma C inside the bag and A comma C outside the bag. If you cannot show such elements, then definitely that relation will become transitive. That's the reason empty relation is transitive. Empty relation can be shown as like this, right? Now you see this relation. Nothing is there. If there is nothing, then you can't violate this formula. To violate this formula, you should have the structure. Definitely there should be one element called A comma B and B comma C and A comma C, which is outside, of course, but so we can't show in empty set. Okay. So minimum relation which violates this transitive property is 1 comma 2, 2 comma 3. Okay. Otherwise 1 comma 2, 2 comma 1. These two are violations of transitive property. The smallest relation which is violating the transitive property is this one, 1 2 2 3. Where is 1 3? No, right? That's why it is not transitive. 1 2 2 1. Then there should be 1 1 according to the definition. That's the reason this is also not transitive. In the exam, they will give you description of a relation and they ask whether that description means transitive or not. We'll see one example. A is related to B if and only if A plus B is even number. Let's take this one. Domain is integers. Okay, integers. Is this relation transitive? Let's see. We know the definition of transitive property, correct? If A is related to B and B is related to C, we have to prove that A is related to C. For that, we have to assume that A is related to B and B is related to C, and we have to prove that A is also related to C forever. Let's try that. Since A is related to B is true, then this is true. Then A plus B is even also true, isn't it? Then I can say that A plus B equal to even number. Now since B is related to C is true, according to the definition, definitely B plus C is even number. If A plus B is even number, B plus C is even number, is it true that always A plus C even number? Let's try. If these two are true, addition also always true, correct? We can do addition always. Let me do it. I am not doing any mistake, right? A plus 2B plus C equal to even plus even is even. Now 2 into any integer is always even number. Whenever some fact is always true, only that facts I am observing and I am taking them, right? I am not taking anything else. Okay. If some fact is not true, don't take it. So here This fact is true, this fact is true, addition is a fact which is always true, that means addition always holds good. Then 2 into b is always an integer whenever b is an integer, that is also a true fact. Then it will become a plus 2 into b is even plus c equal to even number, isn't it? Now a plus c equal to even minus even, right? Even minus even is an even number, correct? So a plus c equal to even. So automatically you are getting a plus c even, and read the definition again. Whenever a plus c is even, definitely a should be related to b. That is a definition of relation, we can't say no, right? That's why whenever this definition is true, automatically a is related to c. Understand? So we'll take one more example. A is related to b if and only if a is congruent to b modulo 5 is a relation. Then is this relation transitive? Here what is unclear is, what is A is congruent to B modulo 5. Unless you know this one, you can't understand what is the relation, right? So that's why. Let me define A is congruent to B modulo 5 in a different statement. A is congruent to B modulo 5 if and only if the difference between A and B, otherwise A minus B, equal to 5 into K, where K is definitely integer. Example. 2 is congruent to 3 modulo 5, yes or no, we'll check. Okay. If really 2 is congruent to 3 modulo 5, if this is true, then this should be true. What is that? A minus b, 2 minus 3 equal to 5 into integer. Let's try. Minus 1 equal to 5 into integer. It is impossible. The reason that integer should be minus 1 by 5, but minus 1 by 5 is not integer. So such integer does not exist. That's why 2 is congruent to 3 modulo 5 is false. If this is false, then A is related to B also false. Finally, according to the definition what we are taking, 2 is not related to 3. Let's take one more example. 5 is, you know, congruent to 20 modulo 5, yes or no? So 5 is congruent to 20 modulo 5 if and only if the difference are 5 minus 20. Anything is okay. 5 minus 20 equal to 5 into k. Let's try. 5 minus 20 is minus 15 equal to 5 into k. Yes, such k is minus 3. When such k exists, then this will become true, so that this is true. If this is true, then this is true. Hence A is related to B. So 5 is congruent to 20 modulo 5 is right. That's why 5 is related to 20 according to the definition. Now the question is, such relation is transitive or not? Let's try. We have transitive definition. Let me write it. What is that? A is related to B and B is related to C. Then we have to prove that A is related to C always. If A is related to B, then then when this is true, I have to take it as true, right? If I take it as true, then this will become true, and when this is true, then this is true. Indirectly, A minus B should be 5 into K, isn't it? So A minus B equal to 5 into integer number 1, because I am going to use K one more time. That's why let me take K1 and K2. Let's say take here. I'm going to use K again. B is related to C if and only if this is true, B minus C equal to 5 into K2, where K1 and K2 are integers. Okay. Using this, can we get any information about A related to C? That means when A related to C, to prove that A related to C, we have to prove that A minus C equal to some 5 into K. This is what our target. My strong feeling is this is possible. This is always true. Okay. So try to think in that way. Somehow try to get a relation between A comma C. Can we get it? Yeah. By adding this, probably you can get a relation between A comma C. What is that? A minus C equal to 5 into K1 plus K2, where K1 plus K2 is another integer. Let's say K. Then 5K. A minus C equal to 5 into K. What I want to say is, whenever this is true, then definitely this is true. If these two are true, automatically A minus C equal to 5 into K, which is what, that is what we proved. So this is transitive. Understand? Let's take one more example. S1 is related to S2 if and only if S1 is subset are equal to S2. Let me take this one, where domain is, we know that set of sets. Okay, set of sets. Write the definition. If S1 is related to S2 and S2 is related to S3, then we have to prove that S1 related to S3, isn't it? Let's come to the definition. If S1 is related to S2 is true, definitely this should be true. That is S1 subset are equal to S2. If S2 is related to S3 is true, then S2 is subset are equal to S3. Then automatically S1 is subset are equal to S3. Okay. So why? So I am going to prove that whenever this is true, automatically this is true. Okay. Why not this is false? Okay, this is called proof by contradiction. First assume that it is false, but these two are true. Okay, so what I am going to do is, by assuming these two true and I assume it as false, then I prove that this case never arises. Let's do it. If really S1 subset are equal to S3 false, then S1 should not be subset of S3, correct? Then definitely there should be one element in S1. Let's call him Raju. So generally I take persons names, to connect to the problem easily. Let's say S1 is some collection of people. There is a person called Raju who is in S1 but not in S3. That is the only reason S1 is subset are equal to S3 wrong, isn't it? Definitely there should be one special person who is not in S3. Remember. Now come back to premises. Whenever you take such person, what happens, you see, premises will not agree, right? So since S1 subset are equal to S2, if S1 contains Raju, since S1 is subset of S2, definitely S2 also should contain Raju. No doubt on that, isn't it? That is a fundamental definition of subset. Now, if S2 contains Raju, that is what we had now. If S2 contains Raju, according to this statement, if this is really true, then Raju also should come to S3. That is what, again, subset relation. If S2 contains Raju, S3 should contain Raju. Then only S2 is subset are equal to S3. Then automatically S3 gets Raju. Saying that S1 contains Raju but S3 does not contain Raju is impossible, right? To have that, definitely premises should be wrong, correct? But we know that to prove some statement false, premises should be true, conclusion should be false. This is impossible. Whenever you make conclusion false, automatically my premises also, becoming false. That's why I can say that you never get true false case. We tried but we failed. You remember it. Okay. That's why this relation is always transitive. So whatever the method I used, that is called proof by contradiction. I assumed some initially that statement is false, overall statement. But later on I realized that statement is not false or assumption is wrong. This is called proof by contradiction. Given a relation of description, how to check whether it is antisymmetric or not, we'll see now. Okay. Example, A is related to B if and only if A divides B. Okay. I will explain you what is A divides B. Let me explain you what is A divides B. A divides B is not as you are thinking. So this is a different symbol I am using. Let me define it. How I use it is like this. A divides B if and only if A into K equal to B, where K is integer. Okay. We spent some time on understanding this one. A divides B. We write this as A divides B. Okay. Whenever you want to say A divides B, this condition should be satisfied. A into K equal to B. Let's ask this question. 2 divides 4 if and only if, according to this definition, 2 into K equal to 4. Where K is 2, it is possible, isn't it? That means 2 divides 4 is true. Similarly, 3 divides 9 is true. But 9 divides 3 is false. 9 divides 3 is true if and only if 9 into K equal to 3, that is absolutely false for integer, correct? So K will be 3 by 9, which is not an integer. That's why this is false, then this is false. So 9 divides 3 is false. Such a relation is antisymmetric or not? Let's do it. According to antisymmetric property, what's the definition of antisymmetric property? if A is related to B, B is related to A, then we have to prove that A equal to B, isn't it? Let's try it. If you prove it, then we are satisfying the definition of antisymmetric property. What's the information you can have from A is related to B? We know that A related to B if and only if A divides B. Then I can write A divides B. But whenever A divides B, then A into some K, let me take K1 because I am going to use one more integer here. That's why I am taking here K1. A into K1 equal to B. If B relates to A is true, then B divides A. So B into K2 equal to A, isn't it? Okay. How to get a condition between A comma B? For that what I do is, first I will get K1 K2 values. Let me multiply them. A into B into K1 into K2 equal to A into B. What is the activity I did here? Multiplication. We know that when you have two equal equations, when I multiply them, like LHS side and RHS side, if I multiply, you get again same equality, right? So A is cancelled here, B is cancelled here, right? So whenever you are cancelling the numbers, be careful. We can't cancel zeros, right? So let me fix the domain. Domain is, let's say, other than zeros, okay? Any real number or integers, right? Okay, for integers other than 0, that is what my domain. So for that, at least this relation holds good or not, we'll see. If I take integers minus 0, then I can cancel AB here, AB, and I get K1 into K2 equal to 1. But there are two cases for K1 into K2 1. One is K1 equal to K2 equal to, since they are integers, minus 1. Second one, K1 equal to K2 equal to 1. There are two possibilities. Okay, let's take one by one. Let's take K1 equal to K2 equal to 1. Then what happens, we'll see. If I take K1 equal to K2 equal to 1, then let me substitute them into equations like 1, comma 2. We know that A into K1 is B. Since K1 is 1, then A into 1 equal to B, then you get A equal to B. But don't be happy, because we have one more case called K1 equal to K2 equal to minus 1. If I substitute K1 equal to K2 equal to minus 1, I may get A equal to, A not equal to B. So we have to try all possibilities. Okay, this case is over. Let's take K1 equal to K2 equal to minus 1. Substitute it here. Then you get A into K1 value minus 1 equal to B, you get. So let's substitute here also. Actually, we have to substitute here also. B into K2 value minus 1 equal to, A. But both are same, you see. In both places you got A equal to minus B, B equal to minus A. Of course, both are same, which says that A not equal to B. So what I want to conclude is, initially I took A related to B, B related to A true at a time. Then I got these equations and I got a K1 value, K2 value minus 1. Second one, K1 equal to K2 equal to 1. Understand my point? Then in one case you are getting A equal to B. In another case you are getting A equal to minus B. That means what? Whenever A is related to B, B is related to A, saying A equal to B is not always correct. Sometimes it may be false. Then you have violated the rule of antisymmetric property. That's why on integers, if you remove 0 also, that domain cannot satisfy reflexive property, correct or not? So that means on integers other than 0, this relation whatever we have defined is not antisymmetric. So sometimes may not be antisymmetric, correct? So we'll see one more example of relation which is antisymmetric. For that, I take domain as natural numbers. Same relation I take, but I modify the domain to natural numbers. Okay. If I take natural numbers, what happens is, again same concept, equations, everything is correct. You get two cases. One is K1 equal to K2 equal to 1. Second one, K1 equal to K2 equal to minus 1. When you substitute K1 equal to K2 equal to 1, you get A equal to B. When you substitute K1 equal to K2 equal to minus 1, you get A equal to minus B. So, but there is no negative number in our domain, then this case never arises, isn't it? To have this condition A equal to minus B, then if A value 2, B should be minus 2, isn't it? Example, A is 2, B is minus 2, then only 2 equal to minus of B value minus 2 will become 2, correct? Understand? So to have a number which is negative of another number, at least one of them should be negative number, but we have natural numbers which are all positive, then this case never arises. Then only case arises is A equal to B. What I want to say is, when domain is natural numbers, whenever you take A relates to B, B relates to A, then always you get this equation K1 equal to K2 equal to 1, that always leads to A equal to B, but not A not equal to B. Then whenever premises are true, conclusion is true. That's why this relation is antisymmetric. Understand? That means by changing sometimes domain, the meanings will be changed. You should be very careful in the GATE exam. In GATE exam, whenever they give a problem, first see the domain. Accordingly, we should act. Understand? The number of antisymmetric relations possible on set of n elements. We'll see that. Options are 2 power n square plus n by 2 and something. Whatever, doesn't matter. We want to find out number of antisymmetric relations. Okay. As usual, same old technique. I take 3 elements first in my domain. Now any relation is subset are equal to A cross A. Then we have to consider 1 1, 2 2, 3 3, then 1 2, 2 1. Why I am writing 1 2, 2 1 together is, it's a group, right? That means in antisymmetric relation we have a link between 1 2 and 2 1. Similarly, 1 3 and 3 1, 2 3 and 3 2, isn't it? So let me link them. Now the question is, how many different ways you can select them, right? According to antisymmetric property, if you take 1 1, you should take 1 1. That is obvious. If I take 1 1, definitely I take 1 1. So antisymmetric property says that if you take 1 comma A relates to B, let me write it, A relates to B relates to A, we should prove that A equal to B, correct? So this relation or this condition is automatically satisfied by 1 1, already we checked it. So that's why 2 2, 3 3, everything satisfies this condition. You get true, true, true. That's why they don't violate the property. If you don't take 1 1, what happens? A relates to B will become false, B relates to A will become false, false and false is false, then false implies anything, though it is true, false implies true is true according to proposition logic. Okay, so this formula is connected to proposition logic. Please go through proposition logic before attending this lecture. Now if you understand that this formula is not violated by 1 1 at any case, like if you take 1 1 or if you don't take 1 1, then they have two options. Similarly 2 2, similarly 3 3, correct? Then I can say that 2 power 3, 2 into 2 into 2. Now this group, if you take 1 2 and if you take 2 1, what happens? Already we know that property of antisymmetric. If you take 1 2 and 2 1 at a time, what happens is this will become true. Which one? 1 is related to 2, correct? 2 is related to 1, correct? But 1 equal to 2, false. That is what the problem with antisymmetric property. If you take 1 2 2 1 at a time, then definitely it violates the property. Okay, so remember this one. Always I can show this kind of structure whenever a relation is not antisymmetric. Now this 1 2 2 1 generally will have 4 options. What are they? One is 1 2, only 1 2, second one only 2 1, third one 1 2 2 1 together, fourth one nothing. If I take only 1 2, no problem, right? Because if I take 1 comma 2, 1 is related to 2 true, 2 is related to 1 false, correct? True and false, false. False implies anything is true, correct? So premises are becoming false whenever you take only one element like 1 2 or 2 1. Premises will become true only if you take 1 2 and 2 1 together. But at the same time, conclusion also should be true to become overall formula true. But when you take 1 to 2 1, already we know that conclusion will become false. Apart from this one, everything will work out. If I don't take anything, still A relates to be false, B related to A false, false and false is false, but only premises are false. This is not the definition. Definition is premises implies conclusion. Remember, premises implies conclusion. Here conclusion is A equal to B. But conclusion is, now let's write it. Premises are false, implies. Conclusion is A equal to B. So A equal to B false, whatever. False implies false, true. Understand my point? So if I don't take any element, premises will become false and overall statement will become true. That's the reason. So this is also one possibility. There are three possibilities. Apart from 1 to 2, 1, everything is a possible thing. So out of 4 options, one is gone. What is that? Taking 1 to 2, 1 together. Every other possibility should be counted. Then there are 3 such options. 3 into 3 into 3. Correct? Let me generalize this concept to n variables. If you have n variables, what happens is you will have 1, 1, 2, 2, so on n elements. We know that, correct? So they all will have 2 independent options. 2, 2, 2. How many times? N times 2 power n. Into what about the other group? In other group we have pairs. Each pair has 3 options. How many such pairs we have already we computed? That is n square minus n by 2. So each pair has 3 options, then 3 power n square minus n by 2. So altogether 2 power n into 3 power n square minus n by 2. So option B is the right choice. In that way you can compute the number of antisymmetric relations. Let's see asymmetric relations. So a relation is called asymmetric if it satisfies asymmetric property. What is asymmetric property? Is like this. If A is related to B, then definitely B is not related to A. That means B is not related to A. This is what asymmetric property. So in another way, it is A comma B belongs to R, then B comma A does not belongs to R. All are same. We'll see one example of a relation which is asymmetric. Numbers. Let's say natural numbers is the domain. Natural numbers. And let me take less than relation. So this less than is mathematical less than, like generally in mathematics we use it, right? A relational operator. So 1 less than 2, yes, true. 2 less than 3. So this kind of relation. Okay. Now according to the definition, if A is less than B, then automatically B less than A is wrong, isn't it? So that is what definition. If A less than B, here relation is less than. If A less than B, we have to prove that B less than A false. That means B is not less than A. That is obvious. In mathematics already we know that whenever a number is smaller than another number, then the other number, such number B, cannot be smaller than A. Automatically it will become false. So that means whenever left is true, that means A less than B true, then B is not less than A is absolutely true. So that's why it is asymmetric. Okay, this kind of relation like less than is asymmetric. One more example is in set theory. You have, let's say, sets. Domain is sets. Okay, and relation is defined like this. S1 is related to S2 if and only if S1 is proper subset of S2. What is proper subset of S2 is S1 should be first subset of S2, but S1 and S2 should not be equal. Okay. Example 1 comma 2 is S1, S2 is 1 2 3. Then we say 1 2 is proper subset of 1 2 3. That means it properly contained in S2. Whereas 1 comma 2 proper subset of 1 2 is wrong. This is absolutely wrong, because though 1 2 is subset of 1 2 but not proper, that means they are equal. Whenever they are equal, we don't say this 1 2 is properly contained in 1 2. So such a relation, let's say we have, is it antisymmetric or not? We'll see. So what is asymmetric? What is asymmetric property? It is like this. If A is related to B, then we have to prove that B is not related to A, isn't it? Okay. Can we prove it or not? We'll see. For us, elements are sets, right? Whenever S1 subset S2, okay, we have to prove that S2 is not subset of S1. That is obvious, right? Whenever S1 is proper subset of S2, so we should have definitely S2 is not proper subset of S1. Understand? So definitely it is true. Whenever left is true, This is true, this is automatically true, no doubt on that. So that's why these two relations are examples of asymmetric property. So these kind of relations are asymmetric. Let's see one counting problem here, that is the number of asymmetric relations possible on set of n elements. Okay, so we have seen so many such problems. Let's use same technique. First I take a equal to 1 comma 2 comma 3, then a cross a will be 1 1 2 2 3 3. Okay, after that groups, one is 1 2 2 3 1 2 2 1, sorry, then 1 3 3 1, then 2 3 3 2, three groups, right? Okay, how to pick these elements such a way that the corresponding selection is asymmetric. Let's start with 1 1. Write the rule. What is the rule? If a comma b belongs to R, then b comma a does not belongs to R. Always remember this rule. We can't violate this rule. If I take 1 1, what happens? We'll see. If 1 1 belongs to R, that means I am trying to take 1 comma 1. Is it okay or not? If I take 1 1 according to the definition, this will become true. Then b comma a, which is again 1 comma 1, should not belongs to R. That is what the rule says. Okay, then already 1 1 is in R, then this will become false, isn't it? So automatically whenever you take 1 1 into the set or relation, premise will become true, conclusion will become false, then rule will be violated. Whenever you take 1 1, it happens. That means what? We can't take 1 1 forever. Okay, now similarly 2 2, similarly 3 3. That means in asymmetric relations 1 1 2 2 3 3 are not allowed. Please recall that another similar relation, that is anti-symmetric relation. In anti-symmetric relation, what happened? We have two options for 1 1 2 2 3 3. Okay, apart from that, that's a relation between anti-symmetric and asymmetric. In anti-symmetric, this kind of reflexive elements have two options, but in asymmetric we have only one option, that is rejection. Now what about 1 to 2 1? We'll see. Recall anti-symmetric property. In anti-symmetric property, if you take 1 2, you should not take 2 1. If you take 2 1, you should not take 1 2, and even we can ignore 1 2 and 2 1. Remember it. So let's come to asymmetric. What asymmetric says is, if 1 2 belongs to R, let's see this. I'm writing it again. If a comma b belongs to R, we have to prove that b comma a does not belongs to R, isn't it? Okay, if I take 1 2 here, then 1 2 belongs to R. I am taking 1 2 and 2 1. I am trying to take 1 2 2 1. According to the rule, if you take 1 2, then this will become true, and if you take 2 1, then 2 1 does not belongs to R is false. That's why don't take it. It's exactly like anti-symmetric property. This also says if you take 1 2, you should not take 2 1. If you take 2 1, then you should not take 1 2. That is what this rule says. Finally, this rule says don't take 1 2 and 2 1 at a time. So if I don't take anything, what happens? Example, if don't take 1 2, don't take 2 1. Now AB is for me 1 2. 1 2 belongs to R, false. If I don't take 1 2, then false implies anything is true, correct or not? Then if I don't take 1 2, anything can be possible. That means if you don't take 2 1 also, no problem, right? You get false, false case, false implies false, true. Understand? What I want to say is, other than taking 1 2 2 1 together, whatever you do, rule will be satisfied. That is what I want to say, right? Then finally, there are three options for each such group, exactly like anti-symmetric. Understand my point? So the relation between asymmetric and anti-symmetric is important. So in anti-symmetric, reflexive elements have two options. Asymmetric has only one option. Other than that, for this kind of elements, asymmetric and anti-symmetric has same number of options. Then that number of options are 3 into 3 into 3, so on. How many times? Here 3 times, of course, right? Let's generalize it. In general case, again you have two cases, right? Your A cross A contains n square elements, isn't it? Out of them, this n elements are reflexive. This n square minus n by 2 groups, right? We know that groups concept, everything. So every element here has only one option. We have to reject it. Now only options we have for real options, I can say. We have real options for only these groups. Every group has 3 such options. Then 3 into 3 into how many times? N square minus n by 2 times. That will become 3 power n square minus n by 2, isn't it? So that's why the formula for asymmetric relations is 3 power n square minus n by 2. Okay. Let's see irreflexive property. Irreflexive property is like this. For every element belongs to your domain, A comma A should not belongs to your relation. Please recall reflexive property. In reflexive property, for every element belongs to your domain, A comma A should belongs to relation. Here, A comma A does not belongs to relation. That's the difference. Let me write it in formal way. For all A belongs to your domain, A comma A does not belongs to R. This is irreflexive property. Understand? Let's see example. Your domain A equal to 1 comma 2 comma 3 and your relation R is, let's say, 1 1 2 2 3 3. This is an example of reflexive relation, isn't it? But this is not irreflexive because we should not have 1 1 2 2 3 3, but we have all. So definitely it is not irreflexive. One more example, R2, let's say, empty. Do we have 1 1? No. Do we have 2 2? No. Do we have 3 3? No. That's why it is irreflexive. Understand? So what about R3, which is 1 comma 2, 2 comma 1. Yes, this is again irreflexive because 1 1 2 2 3 3 are missing. You can have any other element, not a issue. The definition says that you should not have any A comma A. Understand? Let's see one example like a description. They give you a description and they ask whether it is irreflexive or not. Example of such description is subset are equal to A is subset are equal to B if and only if A is related to B. Let's take this relation definition. A related to B if and only if A subset are equal to B. Definitely it is not irreflexive. The reason, every set is subset are equal to itself, isn't it? That is what should not happen, right? So A is subset are equal to A, but we know that A is subset are equal to A if and only if A is related to A. That means according to the definition, that means A is related to A. Understand? But I have to prove that A is not related to A. That means A comma A does not belongs to R is our intention, but I have A comma A belongs to R. So such relation is not irreflexive. Understand? Now we'll see some problems related to this irreflexive property. That is, of course, counting problem. The number of irreflexive relations possible on set of n elements. Let's begin with same argument A equal to, let's say, 1 comma 2 comma 3. Okay. Then A cross A contains 1 1 2 2 3 3. And one thing, this irreflexive property depends on a concept of A comma A, right? That means it is not depending on the groups. Like if you have AB and BA, then you have any such relation? No, right? That's why here groups are not required. I can write them separately. 1 2 2 1 1 3 3 1 2 3 3 2. So they don't have any impact on the relation. So only these three things are very important. We should not take them. Without taking these three, you can do anything. Then I can say that how many different ways you can take these elements, that matters. Then how many different ways you can do that? Every element has two options. You have 6 such elements, then 2 to the power of 6. Let's generalize it. In general case, you have n reflexive kind of elements. That means A comma A kind of elements. And n square minus n other elements. So out of them any subset you can take. How many subsets are possible for any n square minus n elements? 2 power n square minus n. Correct? That's why there are 2 power n square minus n subsets possible for this n square minus n elements. That's why every subset is a relation which is irreflexive because you are not taking these people. Isn't it? So the answer is 2 power n square minus n. The number of irreflexive relations are 2 to the power of n square minus n. Let's see some problems related to this, whatever the concepts we have studied. These statements, if you understand, if you solve them, then probably you can thoroughly understand the definitions of each and every property. If a relation is not symmetric, then it is asymmetric. Read carefully. Given a relation is already not symmetric, then can you always say it is asymmetric? That's the question. Okay. So how to approach this kind of problems, I will tell you. This is P implies Q kind of statement. Whenever you have P implies Q kind of statement, to prove that it is always true, whenever P is true, Q should be true. That's it. Whenever P is true, Q should be true. We'll try whether it is always correct or not. What is P is this one. A relation is not symmetric. What is Q is, it is asymmetric. Okay. Let me take P as true. Okay. If I take P as true, then your relation is not symmetric. Think about a relation which is not symmetric. We know what is symmetric property, isn't it? To have symmetric property, for every two elements, whenever AB is belongs to R, BA should be belongs to R, correct? What if I have a relation where AB is here, BA is here? Definitely it is not symmetric. So I am covering all possible relations which are not symmetric. Okay, any relation is not symmetric, definitely it will have this kind of elements. Agree? Now this is called structural reasoning. Now it is asymmetric. Such a relation, is it always asymmetric, is a question. By seeing AB inside, BA outside, then you might think it is asymmetric, but you are not thinking about other elements. This relation might have other elements. That other elements might be arranged such a way that it is not asymmetric. Is it possible? Yes, definitely it is possible. What if I have one more element called BC and its counterpart CB, both are present in your relation? What happens, you see? With respect to these two elements, your relation is not symmetric. It doesn't mean that automatically it is asymmetric. The reason, there might be two other elements who are symmetric. I mean, who have BC and CB. That means who satisfy symmetric property. Then what happens? This overall relation is not symmetric because of these two and asymmetric because of these two. Understand? So this is finally, whenever premise is true, conclusion is need not be true, right? Conclusion can be false. We proved it. So this statement is wrong because the statement is talking about every possibility. In every possibility, your relation should be asymmetric. No, sometimes it is not asymmetric. Let's take one more example. If a relation is not reflexive, then it is irreflexive. Same argument, we have to assume that relation is not reflexive and we have to prove that it is always irreflexive. Let's try that. Let's take a bag. On that bag, I take a relation which is not reflexive. Why a relation is not reflexive? Try to think about a structure which is not reflexive. For that, definitely we know reflexive property. Reflexive property says that you should have A comma A, B comma B, C comma C, so on, correct? What if I don't have 1 comma 1 in any relation where domain is, let's say, 1 comma 2 comma 3? Definitely such relation is not reflexive. Now such not reflexive relation is always irreflexive. What is the irreflexive definition? Irreflexive definition is a relation is irreflexive if it is, for every element, every reflexive element is absent. That means A comma A, B comma B, C comma C, everything should be absent. But you know that only 1 comma 1 absent. You don't know about 2 2 3 3. What if 2 2 present? If 2 2 is present, then definitely this relation is not irreflexive. But the statement claims that it is always irreflexive. Don't decide based on 1 1, correct? There might be some elements which may violate irreflexive property. That's why, yes, there is a relation which is not reflexive because of 1 1, but it doesn't mean that it is irreflexive. It might be not irreflexive too, isn't it? This is an example. So whenever you have a statement, to prove that that is false, one counter example is enough like this. This is called counter example. So this is also a counter example. Okay. So this is called denying some statement with counter example. Let's take one more example. S3. If a relation is symmetric and transitive, then it is reflexive. Is it true? We'll see again. Here premise is being relation symmetric and transitive. That means you have to take a relation which is symmetric and transitive. Let me take a back and let me take a relation which is symmetric and transitive. Okay, I will take it. Can you guarantee that it is always reflexive? For easy understanding, let me take domain as 1 to 3. Okay. Now let me have some symmetric relation. What is symmetric property? If you have AB, you should have BA, correct? Okay, if I don't have anything, still okay, right? That means this empty relation already symmetric and it is transitive. It doesn't mean that it is reflexive, isn't it? So premises are true, conclusion is false. Okay, counter example is empty set. Empty set is symmetric and transitive but not reflexive. One more example, just add 1 2. Why students do mistake is they take 1 2 and so since it is symmetric they also add 2 1. They take 2 3. I don't know, because they randomly try some elements. Whenever it is 2 3, they have 2 3. According to symmetric property it should have 3 2. Then slowly they reason like this: your relation should be transitive. For that, for every 1 to 2 1, 1 1 should be present. 2 3 3 2, then 2 2 should be present. See, they are preparing a relation which is symmetric and transitive. Okay, so still they are right. They are forming the statement such a way that premises are true. 1 to 2 1 1 1, 2 3 3 2 2 2. See, 3 2 2 3, then 3 3. In that way they add every element so that your relation is transitive. Now your relation is symmetric and transitive. Then they realize that they have 1 1 2 2 3 3 and they argue that it is transitive. So what I want to say is, why this argument is not enough to say that this statement is true. What you did is you have taken one example where this statement overall is true. That is not sufficient. To prove that a statement is always true, you need a proof, not one example. This is an example. But what was my approach here? I was taking a counter example. To prove some statement is false, I need only one example where that statement is false. So that's why I was able to prove that the two statements are false with one example. But here what you are doing is, you are taking just one example and you are proving that this statement is always true. How can you say that this statement is always true? That is absolutely false. For that you have to give a mathematical proof, that you have to take every structure and for every structure you have to prove it. Then you cannot prove for this structure. What is that? You have a relation where there is no element. Then it is symmetric, transitive. You said what? The statement is true for every case. Then in this case, this is also one of the case. In this case, relation is symmetric and transitive but not reflexive. That means what? Whenever a relation is symmetric and transitive, it is not compulsory that it should be reflexive. Understand?